You can see the screen, right? Let's see. Okay. So today I'm going to talk about stochastic formalism and its applications. Uh, this talk is based on the one work I did with Professor Yanou Cui in preparation. So this is my outline. Firstly, I would like to review the stand co-creation in the cosmology, which is Mukhanov-Sasaki equation for the quantum fluctuation, and its application, for example, on the ice curvature. Then later I would like to review the stochastic inflation formalism. Then I will give you like 3 new applications. Those are published in these 2 years. Then I will go for conclusion. So firstly, as you can see, if before the inflation, our universe can be imaged like this silver ball. It's very small. Then our particle horizon can be imaged like this red circle, right? Then after inflation, this silver ball is the universe will be expand quickly and until become a very larger size. But on the other hand, our particle horizon is keeping in the same size in this conforming space. So in this case, if you have any fluctuation, you can imagine it's a energy density fluctuation or field scalar field fluctuations. I show you as this green curve. If you have a fluctuation, you will be enlarged as well. But on the other hand, at the same point, if this fluctuation is much larger than your observable universe, for example, this particle horizon as shown on the right hand side here, if your universe is very small, you cannot detect, you cannot observe this fluctuation because the fluctuation is much larger. So you can only observe the mean value right here. For example, if you assume this uh, green curve is the field fluctuation, right? On the other hand, doing the expansion of your universe until your universe is comparable to this fluctuation, you can see, for example, right here, the field value is larger, and right here, the field value is smaller. So it means that this fluctuation is re-entering into your universe. Then we so call this fluctuation is subhorizon, all right? So in some case, if your fluctuation is larger than your observable universe, which code is a superhorizon. All right. Then after the fluctuation is re-entering into your universe, it will become the dynamical. All right. Before then, it just looks like a dark energy because we only observe the mean value for this, for example, field value. All right. So in some case, if you have a certain model, then we can calculate this fluctuation. We can do the Fourier expansion to separate these two modes. For example, we can consider the superhorizon modes, but also the subhorizon modes from this field, right? So the superhorizon mode, as I say, it is x independent. It only depends on the time. Then the fluctuation part it depends on your space, right? So in the certain procedures, we can eventually you can find the fluctuation will be the size as larger as the end of inflation Hubble rate, right? This is a standard result for this standard cosmological equation, right? So in this case, if you considering your universe, right? If you take a picture about your universe, you can see somewhere this field value is a smaller, and on the other hand, somewhere the field value can be much larger, etc. Then the difference between them is about a 1 Hubble ray at end of inflation Hubble ray. So take a very simple example. If you have a potential, more very simple example, you have this m squared phi squared term, only have this term, then you can plot your potential to be like right hand side, right? So in this plot, your field value will be located at the initial field value, but also you can have a quantum fluctuation as large as this range. All right. So in this theory, we can predict the initial initial value of a potential, then also the initial field value. But in this case, as I see on the left hand side, because you have inhomogeneous, so this one can be constrained by CMB, right? This constraint so-called iso-curvature constraint. So in this case, this constraint is larger as this size, all right? So in this model, in this most simple model, we have 3 parameters. One is this scalar mass. Another one is initial field value. And the third one will be the end of inflation Hubble rate, right? So we have a 3 constraint. Then if you can assume this field is star matter, if it's a star matter, we can include another constraint by star matter radiative density. So you can simply count, we have a 2 constraint, but we have 3 free parameters. So unfortunately, this model is not very predictable because we can always tune the parameter space to avoid those constraints, right? Because the parameter is more than the constraints. But this calculation math is a standard calculation is widely applied in the literature. For example, some Asian models, right? So this is a review. So the something new is the stochastic approach. Then this green box is correspond to the standard one. Then the red one is the new from Staropinski and Yokoyama. In previous one, we only consider the fluctuation as the subhorizon modes. So which means is we only do the integration part, which is the wavelength is smaller than your horizon, your particle horizon at end of infraction. On the other hand, the Staropinski, they did the same thing, but they just simply add a state function into this fluctuation modes. This state function is the same. They only consider the subhorizon modes in this fluctuation. But the interesting thing is, if you consider the equation of motion, including the superhorizon modes, you will find this is original equation of motion. But after you adding this state function, you will find another term into this equation of motion, right? You just simply do a time differential on this state function, then you can find this f. Okay. So we call this f term as a stochastic variable. Then we find in the classical mechanism, we already this equation of motion is studied. For example, in the Brownian motion, right? They basically have a same form. The A is just a physical quantity, physical degree of freedom. Then V is a velocity. Then you also have a stochastic variable. So they explain basically the same physics. On the right hand side, I show you the Brownian motion right here. The Brownian motion you cannot exactly predict the how move for this for example this yellow ball, but instead you can predict the probability distribution of this motion. For example, initially the ball is right here, right? So you can calculate some probability. It can be here at a certain time. It can be here at a certain time. Have some probability. So how to calculate this one? The logic is very simple. Just for example, if you have a delta t, if you have an initial position, then for example, this one is for first correction, the particle may have a position distribution like this. But on the other hand, if you consider longer time after few corrections, the particle can have some more flat distribution. Then if the time is long enough, the initial condition no longer important, right? Because you have so many corrections, right? So it turns out we can calculate the probability distribution of this ball. You can see where is the ball, but we can only do the probability. So it turns out in field theory, how to mimic to field theory, we only consider one single Hubble patch as a list ball. So we can have a second red yellow ball right here. We can just map this yellow ball in different Hubble patch at end of inflation. So what is a collision in field theory? It turns out it looks like in one single Hubble patches. For show wavelength is correspond to the quantum mode, right? Then the wavelength which is comparable to your Hubble ray, which is so-called the classical mode. Every single time when you have a mode which just leave from your Hubble horizon, we just substitute it into this stochastic term. So you can when you have a second mode who want to leave from your Hubble ray, we just substitute it again, then do the calculation again. Then if we just repeat again, then eventually we can find the distribution of this field, right? In the Brownian motion, we consider the position distribution for the ball, right? But in this case, we find the field distribution, which is like this. If you have a universe, your universe size is as large as this one, right? After the inflation, then you have so many Hubble patches. So many Hubble patches. Each Hubble patch is as small as one epsilon h. H is end of inflation Hubble rate. Then epsilon is one free parameter. It can be order one. So it's not really important. So in this case, we can find a field distribution, field probability distribution. For example, in this Hubble patch, you can have a phi 1. In this Hubble patch, you can have a phi 3, phi 2, etc. Right? So it turns out in this framework, just going to give you the sense is that we have in homogeneous for this field, then it's going to follow this differential equation. Then this differential equation will give you the probability of this field. So it turns out that in this whole universe, it will follow this solution. All right, this is a solution for this differential equation. All right. So this is basically review for the stochastic approach. Then I will give you 3 applications. First one is diameter isocurvature, going to compare the previous case. And the second one will be the curvature fluctuation from Sandbell Higgins plus infraton reheating. Then the third one will be the die-energy one. All right. So in previous study, I want to remind you we have 3 free parameters. But if you consider stochastic, as I mentioned before, it's just like a Brownian motion. So in this case, if you're going to calculate the same potential, then you calculate the energy density for this potential, you'll find, okay, very interesting. The potential energy density is independent to not only the mass, but also the initial condition for this field. Right? It only depends on the HI. So just like Brownian motion, if your inflation is long enough, the initial condition is no longer important. So we basically just delete the initial condition. Then how about the mass? Because here we have a 1 free parameter, right? Then we delete one of them. So here have a 2. How about this mass? Because this equation looks like mass independent. The answer is the mass of this diameter field, the scalar field, will diametrically depend on the energy density of this diameter will diametrically depend on this mass, because as I said in the beginning, your fluctuation, when your fluctuation re-enter into your universe, the fluctuation will be diametrical, right? So it turns out the meaning is like when this diameter wavelength enter into your universe, it will be like diameter. Before then, it will be like die-energy, right? It only being the diametrical after the wavelength enter into your universe. So which means the mass is one or another free parameter. So right now we have 2 free parameters. So we can plot the constraint. We have 2 free parameter. We have 2 constraints. One is from isocurvature bound, another one is relax density of the dark matter. So this part show you very clearly we only have two regions around. One is this overlap, another one is on this corner. So these two correspond to these two parameter space allowed. So stochastic basically can delete the initial condition and make this model more predictable. Not only this model, this one is the most simple example, but mostly people also apply this formalism into, for example, Asian or other popular models, then make them more predictable because they can cancel the free parameter, for example, initial condition. Right? Let me drink the water. Wait a second. Okay. So this is the second example. Also very interesting. This one is so-called a curvature fluctuation and sentimental Higgs. In this paper, they only consider purely sentimental Higgs. Right? All things are the same as sentimental Higgs. Then they also consider infraton. They are considering the reheating part. So in this part, the infraton will decay to other particles, for example, the sand model one. They consider they will decay to the sand model particle, mainly decay to the sand model particle. Then in this case, I just show you the Feynman diagram right on the right hand side. This one is the infraton, it will decay to sand model part. Then we're just going to treat this sand model part as a radiation because at that time the temperature is very high. So sand model particle basically is just like radiation particle. So in this case, as I mentioned before, the cinematic Higgs is a scalar field, right? So it can follow some field distribution around your universe. So for example, in these Hubble patches, the field value, the cinematic Higgs field value can be H1. So H2 here, H3 here. So it follows certain distributions. So for these distributions, you can find the infraton decay to Sennett-Model decay rate because the Sennett-Model fermion mass is from Yukawa coupling. Then if you have a different Sennett-Model Higgs field value, you will change the Sennett-Model fermion mass just simply by this formula. So in different Hubble patch, the infraton can have a different decay rate. Due to this property, in different Hubble patch can have a different expanding rate because infraton is matter line, then radiation is radiation line. So which means in different Hubble patch, they can have a different expanding rate, they can have a different temperature cooling rate. So due to this different temperature cooling rate, we can the temperature inhomogeneous will be consumed by current CMB observations. Because, for example, the CMB observation is delta D divided by T is about 10 to minus 5. So it's this white area. So in this red area is ruled out by CMB current observations. Then on the other hand, this green area is allowed. So they can constrain their model. For example, they constrain the 5-4 theory, Sennett model Higgs 5-4 theory coupling lambda at a very high energy. Depends on your reheating, right? So this, and on the other hand, they also constrain the largest Yukawa coupling in the Sennett model. But this is, the energy is at the end of infraction, so it's much higher than the initial width scale, for example. They also constrain the decay rate, the infraton decay rate to the Sennett model fermions, right? So in this part, you can see that you only have this green region is allowed. Then this black region is correspond to the out of sensitivity to the current observations, right? Okay, so this one is another interesting example. Then the third one is going to we consider dark energy part. Before I start, I would like to give you a review for a scalar dark energy. In most of model, we face two fine-tuning problems. The first one, because the die energy density is very small, so the potential should be very small as well. It's a much smaller than the Planck scale. On the other hand, you can see the equation of state right here. If we want to find the die energy equation of state minus 1, the kinetic turn should be very small. This corresponds to your potential should be very flat. So this one can make sure your kinetic energy of this field can be suppressed, right? So here I show you one example for this classical field theory die energy. You have an initial field value, then you will rolling down on this particle. All right. So if we apply the stochastic approach into this scalar field die energy model, you will find, as we mentioned before, the field will distribute on this potential. So some region, the field will behave as a diameter. Some region, it will look like a slowing down field. Some region, it will look like the die energy. All right. I will mention detail about the slowing down field later, but it's just like exotic component in the universe. It will not be like diameter, it will not be like die energy, but it will is the equation of motion is a time dependent. All right. So if you consider the field distribution like we did before, the distribution will be looks like the left hand side right here. So I just pick up the benchmark for this model. Then you can see most of field are looking like a diameter. Only few fields they are looking like a die energy. Then others like rolling down field. So if you want to plot this distribution in your universe, you will be looks like on the right hand side. Most of Hubble pages, end of inversion Hubble page, they will look like the matter line. Then some of them will rolling down field, some of them will be like die energy. In this model, we don't need to care about the rolling down field for two reasons. The first one is the rolling down field, the particle is not that larger because the die energy part is much larger. Then they both experience the same suppression from the field distributions. So it means that the die energy density is much larger than the rolling down field. So that's why we don't need to care about the rolling down field in this model. On the other hand, the diameter is not be suppressed. So the diameter part is also much larger than rolling down field. All right. So in this model, in this case, the die energy density is the how high for this potential. Then we also consider distribution. Then the suppression part is from this distribution because as you can see, the distribution is is suppressed by this value. It's very small. So that's why we can make this energy density to be this small, even we consider very large potential value, right? Similarly, for the diameter part, the diameter was not suppressed by this distribution, but it will be suppressed by this redshift effect from the standard cosmology. So it turns out that if these two are compatible, which means we can unify the die energy and diameter. We can realize these two in a single model, right? So this potentially solve the answer the die energy diameter coincidence, all right? As I mentioned before, I would like to mention about the rolling down field. In previous case, because we are considering the particle which the die energy region is much larger than the rolling down field region. So that's why we don't need to consider rolling down field. But in some model, for example, Coleman-Weinberg model, in this case, the diameter region is less small. But on the other hand, the rolling down field is quite large. So we have to consider the contribution, the energy budget of this rolling down field. So in this case, the rolling down field will take place in your universe energy budget. then it will badly affect your your prediction of this Hubble ray, right? So this I, they are the current observation, local observation for this Hubble ray. Then we cannot fit this model very well. We cannot fit this data very well because the random field will take place. All right. Then, by the way, this point is so-called a Hubble tension. Even the lambda CDM cannot fit it. Okay. I think if no question, let me go to the conclusion part. We firstly review the standard procedures for the field fluctuation and isocurvature. Then we introduce the stochastic formalism and going to compare the previous case. Then we give the 3 new applications, current applications in these 2 years. First one is applying to more the simple diameter potential. We only consider m squared, phi squared 10. Then this approach basically delete one free parameter, which is the initial field value. Then this approach also be applied in, for example, Asian potential, some popular scalar models. Then this, in the first example, we constrain the diameter mass in this range. All right. Then second example is that we consider infraton reheating plus an interaction with the standard model Higgins. So this one can constrain the coupling between the infraton and the standard model particles. Then also hint the UV behavior of this the largest Yukawa, standard model Yukawa, and the lambda from the 5-fold. Then the third one will be we apply this formalism to the star energy. Then release the one of fine-tuning problem in the scalar dark energy model. Then we also hint we can unify the diameter and dark energy, then solve the coincidence problem. Yeah, I think that's it today. Thank you for listening.
All right, well done. Any questions?
I have a question.